Guys, let's look at this problem right here. His question is asking, what is the thickness required of a masonry wall having a thermal conductivity 0.75 watts per meter Kelvin? If the heat rate is to be 80% of the heat rate through the composite structural wall having a thermal conductivity of 0.25 watts per meter Kelvin and a thickness of 100 millimeter, both walls are subjected to the same surface temperature difference. Okay, so here they are saying the DT is same for both of them. Okay, so just consider that. And first of all, let's put the heat flux equation. Heat flux equation says that Q double prime is equal to K times dt divided by the thickness. Okay. Now here what they're saying is dt is equal for both of them. So we need to rearrange this in terms of dt and create equation for two of them. So here, let's consider the first surface as a Q1 in everything. So Q1, K1, L1, dt is going to be same. So I rearrange this one in terms of dt, which is going to give us Q1 prime L1 divided by K1. Okay, let's call this one equation number 1. And then we know that temperature same for the other one also. So another equation we're going to have Q2 double prime L2 K2. Okay, let's say equation number 2. Since the temperature difference is going to be equal for both of them, we can equalize both of them. So we can say this Q1 prime L1 over K1 is equivalent to Q2 prime L2 over K2. I just equalized equation 1 and 2 because the dt is same for both of them. Okay, now what we can do is we can just we have to solve for, okay, here the provided is they have provided k and then percentage of the heat rate. So they say it's 80% of the heat rate here, and it's 80% of the this one. So it means this is going to be 100% and this is going to be 80%. And then we have to find out this this is not provided. Okay, this one here is not provided, so we need to rearrange the equation in terms of this. So we need to find out this thickness. So this is going to be Q2 double prime L2 over L2 times K1 over K2. Okay, so and also the Q1 multiplies here as well, Q1 double prime. So first, let's analyze this. So first of all, we know that the first thermal conductivity Q1 is 0.75. So I put that one right here, 0.75. And then they have given the L2, which is 100 millimeter right here, 100 millimeter. Let's put the units as well, so we know everything. 75 watts per meter Kelvin, and this one is 100 millimeter. And for the thermal conductivity, uh, we have 0.75 and 0.25 here. Okay, let me make sure if I did everything right. So L1 is going to be, K1 is going to be multiplying that, so we have the K1 on top. Q1 is going to be, I made a mistake here. Let me do this again. Okay, so the equation is going to be basically L1 is on top here, so Q2 double prime L2 and K1 multiply, and in the denominator we're going to have Q1 prime and then K2. Okay, Q1 is nothing but 0.75, so that is in the, I mean, no, K1 is 0.75. K is the thermal conductivity, 0.75 watts per meter Kelvin. Kelvin, and then L2 is provided to us 100 millimeter, and then Q2 prime is so this is the heat He1 prime and Q2 prime are heat comparison, so we do that one later. And then K2 is given to be K2 is the second thermal conductivity. Second thermal conductivity is 0.25. This one is 0.25 watts per meter Kelvin. And here they're saying that the heat rate of the first one is 80% of the second one. So it means the first one is 80%, so 0.8 here. Of the second one is 100%, so we put 1 for that. Now if we solve this, that's going to give us a thickness. So this is like you get 3 here, so 300 millimeter divided by 0.8, and if you calculate that, you're going to end up getting 375 millimeter. Okay, that's the final answer. I hope you guys found this video helpful. Thanks for watching. Don't forget to subscribe my channel. See you guys on my next video.